Number 1. In this question, we're asked to use the idea that when frequency of rotation is decreased, what happens to the output power? So, we've learned that frequency is directly proportional to the output voltage. So when frequency is decreased, the output voltage decreases, which means the current also decreases, which means the maximum power will also decrease. So we expect the Pmax to decrease. Also, frequency is equal to 1 over the time period. So when frequency is decreased, we expect the time period to increase. And when we look at the options, because we expect a decrease, we cancel B and D, and we choose C because one time period for the power graph, since this is a sine squared graph, one period is when the graph has had two maxima. So when you have a power graph, this is one period. This would be half a period, and then the other half of the period on the voltage or the current graph. When it's power graph, you would have two peaks in one period. So since we expect an increase in the time period, it can't be 2, it's going to be the one that's bigger, so we choose C. Number 2, again we have a power graph where we can now see that 0.04 is the time period. We have an AC power supply of RMS value 60 volts. We want to know what are the frequency and the AC power of the AC power supply and the average power dissipated. So since T is 0.04, we can write F equals 1 over the time period. 1 over 0.04 is 25 Hertz. So answer has to be A or C. Then we want to find the average power dissipated. Average power, I can use the V squared over R version because I have a value for the resistance and I have a value for the RMS. And since I'm looking for the average power, this relates to the RMS voltage anyway. So basically you have 60 squared divided by 100. This gives 36. So our answer is A. Question number 3. We have a DC current of 5 ampere. Dissipates a power P in a resistor. Which peak value of an AC will dissipate an average power in the same resistor? Now we know I RMS is I peak divided by root 2. So if RMS value is 5, 5 root 2 is our I peak. So answer would be D. Number 4 is asking, again relating to power, peak value VO delivers average power P. What is the RMS current? So we're looking for I RMS. So now we know the peak, the average power. I'm going to use the P equals VI version for the power. So P for the average, I write with the RMS values for the for finding the average power. So since I'm looking for IRMS, I need to divide the average power P by the VRMS. I have VO. VRMS would be VO over root 2. So we write the same with the ones we are given. When you rearrange this, you get C for the IRMS. Now, number 5, we now have a current versus time graph. The maximum value of this graph will obviously be IO. We have a resistance of 2 ohms. We're looking for the average power. Since we have resistance and current mentioned in the question, for power, I'll simply use the I squared over R version. So since I'm looking for average power, this relates to the I RMS squared times R. I RMS is IO divided by root 2, so 4 divided by root 2. This is being squared times the resistance of 2. When you rearrange this, this is 16 over 2 times 2. You get 16. Answer is C. Next question, number 6. Two identical resistors are connected in series. Let's do a quick diagram here. Let's say these are R and R connected to an AC power supply. So this is what my diagram would look like. Obviously, because they are in series, they would have the same current. And we're looking for the maximum power in one of them. And the power supply has an RMS value of V. So, and we're looking for an RMS current of I. Now, P, since now we're relating to V and I, I'm going to use the P equals VI version. The question is asking for the maximum value, so I will use the peak values to relate to that. In each, the P max is going to be the peak voltage, which is going to be, well, since V is the RMS, peak will be V root 2, but half of it, because that's the main total voltage, and half of this is the peak voltage of the whole circuit. Since these are in series, they're going to share. So this is the voltage on each, and the current is the same. I is given as the RMS current, so IO will be I root 2. When you rearrange this, the root 2 times root 2 will divide by 2. It will cancel, so we have V times I. Our answer is B. The next question is in number 7. We have a graph of power versus time again. Obviously, how we read this graph, this is the maximum power. And we know the average power is half of the maximum power, so it's going to be 60 watts. To find the time period on a power graph, we look for when it completes 2 peaks. So that's the time period. What is the question asking? The average power produced and the period. Well, we just found them. We know this is 60 and the period is 10. So our answer is B. Next question says question number 8. RMS value is 110. What is the maximum? So we know VO is going to be 110 times root 2. Now this is a multiple choice question. You cannot use your calculator, but you can use your common sense. So estimate and eliminate. This is obviously not twice 110. It is not equal to 110, and it's not less than 110. Our answer is B. Next question. We have a coil that rotates in a magnetic field. This is number 9. Which of the following gives the RMS value and the frequency of rotation? So this graph completes one cycle in T. So we know frequency and period are related as such. So the frequency will be 1 over T, and the RMS value, this is the peak. So peak divided by root 2. Our answer is given in D. Peak divided by root 2, and frequency is 1 over T. Number 10. This one is about knowing the terminology. RMS current rating is 4 ampere. So when we see this, we should know that the direct current equivalent is the same thing. Our answer, straightforward, is 4 That's as given. We should know that these mean the same thing. Okay, number 11 and 12 are about diodes. So number 11, we have a diode bridge rectification circuit and alternating potential differences applied. So we're supposed to choose the correct statements among these options. So let's see what happens in this circuit. When M is the positive and N is the negative terminal, this is what we have. So current, it will have to go through Q, go towards the left, and come back down here, and then complete the circuit. So that is half of the time. And it's like that because when you come to this junction, P doesn't allow you to go left. When you come to this junction, R forces the current to go that way, and to come back, it needs to come back this side. Let's use a different color to see what happens when the polarity switches. Now we'll show the current starting from N. Let's go and reach this junction. Now we have to go through R. Q prevents me from going that way, so I go left again and then come back on through P and reach M, complete the loop. So we know when P is working, R is working. So P and R work at the same time. S and Q work at the same time. So when P conducts, Q does not conduct. That is correct. When S conducts, neither P nor R conducts. When S conducts, P and R do not conduct. That is correct. The direction of conventional current in the resistor is from left to right. You will see that no matter which polarity M and N are, the current through the resistor is always towards the left, so from right to left. So this statement is not correct. So our answer is A. The last question on this worksheet, number 12. This has an input to diode bridge rectification circuit with a time period of 20 milliseconds. We're looking for the V versus time graph. Since this is full wave rectification, the original signal would be a sinusoidal function. When it is rectified, you have this and this corrected, and then this, and then this. So that is either in A and B, but the difference between A and B is the time period. We are given that time period is 20, so we need to choose A, because in one time period you have two of these bumps when it is rectified. So that's the correct answer. And now the last question. In number 13, which diode bridge is used as a full wave rectification? Answer is A. You can find this by trial and error. These diode directions are given. In every one of these, you will find that it gets blocked. Like let's try B. You have like which way do you go? These are connected wrong. One of them must face in, one of them must face out. So it needs to be forcing the current in a particular direction. Same problem here. They both, but like this can't go anywhere, any one of these. And in here, the problem is here they face the same way out of that junction, so that doesn't make sense. See, when you look at A, when current comes in, it has a single direction to go, and then when you come here, it has this direction to come back. And on the other direction, here you have a particular direction to go, and you have a path to come back, so 13 is A.